This video is about perpendicular lines, and this material is found in your text in section 2-5. The perpendicular lines theorem is a theorem that I'm going to name the perpendicular lines theorem. What I'm really doing is combining your book theorems 2-4 and 2-5. I'm combining them because an if and only if statement can actually cover two if-then statements. So I've combined the two if-then statements in these two theorems into an if and only if statement. Two lines are perpendicular if and only if they form congruent adjacent angles. So that can tell us two things, depending on what information we start with. Suppose we're told that angle 1 is congruent to angle 2. This theorem allows us to conclude that these two lines are perpendicular because there are two lines intersecting at a point that are forming congruent adjacent angles. Therefore, the two lines are perpendicular. But suppose the problem statement only tells us that the lines are perpendicular. It could tell us that in words, or it can tell us that just by marking the diagram with this symbol for perpendicular. What can we conclude from that? Well, we can conclude from that these lines form congruent adjacent angles. So the theorem goes both directions, and in fact all four of these adjacent angles are congruent because they're formed by two perpendicular lines. Let's do an example problem using perpendicular lines. Suppose we're told that the measure of angle ABD is 6x. The measure of angle DBE is 3x plus 9. Measure of angle EBF is 4x plus 18. The measure of FBC is 4x. And I'm also told that ray BD is perpendicular to ray BF and that ray BE is perpendicular to line AC. That's a lot of information, and it's probably more information than we'll need to solve this problem. So I'm just going to pick two adjacent angles and see if I can find x using only two of these. I'm going to pick angle EBF and angle FBC because I know that their measures must add up to 90 degrees. So I'm going to say the measure of angle EBF plus the measure of angle FBC must equal 90 degrees. Substituting in what I know about those angles, I'm going to say 4x plus 18 plus 4x equals 90. Therefore, 8x plus 18 equals 90. Subtracting 18 from both sides, I have 8x equals 72. And dividing both sides by 8, I have x equals 9. So here I only had to use the fact that perpendicular lines form a 90-degree angle. I didn't really even need to use the fact that perpendicular lines form two congruent adjacent angles, although that fact might come into play in other problems. You try this problem using the same diagram. Here's another example. Suppose we're given that line BF is perpendicular to line AE. We want to express in terms of x, y, or both the measure of angle COA. Now, in terms of x, y, or both, tells us that the kind of answer we're looking for will not necessarily be a number. the answer that we're looking for could have x's or y's or both in it. So since we want the measure of angle AOC, since we're told that this line is perpendicular to this line, in other words, angle AOB measures 90 degrees, we can simply use the angle addition formula to say 90 plus x equals the measure of angle AOC. Now that seems pretty easy. Have we answered the question? Well, we were asked to express the measure of angle COA in terms of x, y, or both. Note that angle COA and angle AOC are in fact the same angle. So we have found the measure of that angle, and we found it in terms of x, y, or both. So we're done. You try this one using the same diagram. Here's another example for you. Suppose we're told that the measure of angle 1 is 46 degrees. The measure of angle 4 is 44 degrees. Can we conclude that ray XY is perpendicular to, this is a misprint, this should be ray XZ. Can we conclude that those two are perpendicular? Well, we're definitely not given a right angle sign, so we can't conclude that just by looking. We do have a straight line here, so we might be able to employ what we know about linear triples, the word that we invented in class. Because angle 1, angle 4, and this angle, angle YXZ, form a linear triple. So we can say that 46 degrees plus whatever the measure of angle YXZ is plus 44 degrees must equal 180. Is that enough to make any conclusion? Well, we can certainly find the measure of angle YXZ. If we do some algebra and subtract 46 and 44 from both sides of the equation, we have the measure of angle YXZ is 90. Another way to say that is that ray XY is perpendicular to ray XZ. So yes, we can conclude that XY is perpendicular to XZ. For this example, I want to show you an applet that I made on GeoGebra again. If angle 2 is congruent to angle 3, can we conclude that ray XY is perpendicular to ray XZ? Sometimes I like to construct an applet in GeoGebra just to do a mental experiment about this. Does the fact that these two angles are congruent, make these two rays perpendicular? So let's look. Oops. The way I constructed this diagram was I constructed it such that angle 2 and angle 3 must always be congruent. And I'm going to drag around these points. You can see angle 2 and angle 3 look like they're both staying congruent, but does it look any more like ray XY is perpendicular to ray XZ? No, they sure don't look perpendicular. So you can even do a mental experiment like this to prove to yourself that something's not necessarily the case. Try this one. If angle 1 and angle 3 are congruent and complementary, can you conclude that ray xy is perpendicular to ray xz? Try this one. If angle 1 is congruent to angle 3 and angle 2 is congruent to angle 4, can you conclude that ray xy is perpendicular to ray xz? For further practice, see page 52 of your book, most of the odd problems listed here.